somewhere and it feels fantastic, rolling across the terminal floor.
What's popping, gamers? Jump right here. Yeah, I had to make that 3 blue 1 brown quote at the beginning joke. The quote was, will be here somewhere, I hope. Is it? Here it is. It's basically just about data structures and algorithms and sort of how the two make up programming and how data structures should be of a higher priority than algorithms. Just I thought it was cool to put this up. I don't know if that worked or not, but there you go. So essentially, I've got a stream today until I've got an upper limit of 7:15, so I've got an hour still, which is good because I have a lot of things I'm trying to throw in, but this will be alright. Give it a bash. Yo, hey Ali. Alright, where's the slide? Oh gosh, is this the slide? Here it is. So this is the plan. So we've got 7 things on this side, 3 things on this side, and then I realized as I'm going to go along there's probably going to be extra things. And also, just to clarify, we're not going to be going over recursion, but everything else within the procedural paradigm. And just to clarify what that is, where is it? Here it is. Just to clarify what that is, that's this. We're looking at imperatives in this 5-part series, and today we're looking at a really important part of that procedural paradigm. This is essentially all programming, really, except for object-oriented, but that sort of extends onto procedural, like as an add-on top layer. But for the most part, it's all procedural programming. That's what we're going to be looking at today. So I've seen a lot of other videos do it as like 3 parts of procedural paradigms. You've got selection, iteration. Oh, one more thing before I begin with that, actually. I'm sure you already saw it at the beginning, but I guess I'll just reiterate just because it's important, is that this video is like very much required. I'm going to be building on this heavily. And even with this, there's a chance you might get lost, but hopefully I'll try and keep you on board. But without this, it's like game over. So if you've not seen this video, I would go and watch that first. But assuming you've watched that video or you know sort of roughly how a computer works in a fair bit of detail, then we can continue. So you see a lot of people try and cover this topic of how do I program with 3 sections of selection, iteration, sequence. But essentially when I was looking at that, oh, and also some other people do like 11, 10-part video series. I sort of wanted to bring the 2 together and have 1 video, but like 7 parts rather than 3 because I felt that worked a bit better. And in chat, if you have any questions at any point, feel free to ask anything. So I'm going to go through these, but before we just jump straight into programming and figuring out what's going on here, I guess I just wanted to start with why program. And I guess the idea is that all programming can be split into one of these 3 different types. So you can either do programming like we discussed in the last video to make the computer do calculations, but you can also like just do calculations, like if like say we had some maths problem, we needed to calculate the answer, you could use programming just to solve maths problems. Then the other 2 that people are sort of more familiar with are utilities or entertainment. So like right now, this like drawing software I have is a utility. And like even though it doesn't seem like a maths problem, the idea is that fundamentally it is. And same with entertainment, which is essentially just video games. Even though it doesn't seem like it's a maths problem, fundamentally like all programming can be boiled down to just a maths problem. And although what I'm going to be saying here applies to these 2, because we're going to be doing maths and the maths applies to these 2 as well, we're going to be having a focus on maths because I think that's probably easier to begin with and why you see a lot of people starting with doing the maths. But then sometimes people feel it doesn't relate to coding like programs that are bigger, but it actually does, it all scales up. Yeah, like calculating the power of 2 modulo 97, which is the example we did in the last video, as Keishi said in chat. Alright, so I guess we begin on this 9-part series of 9 parts. So first of all, we're going to be like taking the model from the previous video Oh, I should have shown the model by now, but it's okay, we can show the model now. Where is it? Here it is. So we looked at this model, very important. I'm assuming you know exactly what's going on here because I did it a lot in the last video. And I just redrew it because it was getting a mess. Is it here? No, why did I redraw it? Oh, here it is. Because it was getting an absolute mess, that was slide. So we're going to be using this one as a reference. So as we spoke about in the previous video, it's like you store your program in here, and then you load it into here, and then execute. So we gave an example of code, but I guess now we're going to be doing another example of code, but here instead of just roughly talking about code, that's going to be the focus. So let's write a computer program. So bearing in mind this is how a computer works, we should be able to give the computer calculations to do, right? So if I give some examples, so everyone's got any things they want, but we could say, hey computer, what's 5 plus 7? What's, I don't know, 2 to the power of 10, 2 times 10 to the power of 60, like a standard form thing, divided by 3 or something like that. We could do 15 modulo 4 or something. And in theory, right, we should just be able to give it calculations. That's what we've said a computer does. It takes a bunch of things to do and it does them. So you'd think, right, that if we just save this on the hard drive as we spoke about we need to do last video, call this program1pog.py, and if we execute it, we should get those answers, right? Oh gosh, come on computer. Yeet. But as you can see, nothing happens. And so obviously the question is, why did nothing happen? But actually a more important question is, did nothing happen? And the idea I want to put forwards here is that even though, right, it doesn't seem like anything happened, I'd like to put forward the argument that actually it does. So where's my example? I wrote this example, but it's not very good. I'm going to write another one on the fly. And I guess the best way, I would say, to show that this is happening, which I thought of just like 10 minutes ago, is like this. So you can ignore this as a function, we'll look at that very shortly later. But essentially, right, if we have a thing that does a calculation, if we just do the calculation and print it out, we'll get the calculation out. Oh gosh, I'm definitely lost some people, but print moment, let's go. That's the main reason why programming was created. Yeah, that's fair. Although I feel like to begin with it was to do calculations, but eventually we realized we could use those calculations to do things that anyone can interact with, which is what computers are now, I guess. So as you can see here, we print out the calculation. If my computer can compile code, there we go. But even if we got rid of the print and we just had calculate, like my argument is even though we're not getting anything out, it's still doing the calculation. This is still being executed. So in this case, even though it doesn't seem like anything's happening, fundamentally these calculations are still happening, it's just they immediately disappear. So that's sort of the first stage of our adventure in programming, is just we apply the model directly, we give the computer calculations to do, so we give this one a tick. But obviously that's not very useful, and the reason why it's not very useful is essentially with this model, we're paying a lot of attention to these 3 parts, but we're ignoring this part, and we need to pay more attention to that part. So let's pay some more attention to that and bring in some input and output. And this relates into episode 2 on functional entities of input and output. We need input and output to make the program meaningful. Like here we have input, but we have no output, so hence it doesn't really do a whole lot. So to do that, we're going to look at our next step of programming. We're going to look at sequence calculations, which is essentially we'll do what we did here, but we bring in input and output. And the way we do that is we need to bring in variables. I could spend a lot of time talking about variables, but I know I shouldn't because it's not as advanced as I feel it is. But let's bring in some variables. So essentially what we can do here is we could just straight up output, so we could just tell the computer for each of these calculations you do, output it, and print is what we use for output. This is a procedure, we'll be talking about procedures more later. But essentially what a procedure is we'll talk about side effects as well. Side effects are important and you understand it better then, but for now just think about it as this is telling the computer do this, just put it in the, we call it, where is it? The shell somewhere. Where's my shell? There it is. This is the shell, and essentially print just means put whatever I put next into there. So saying put the output of 5 plus 7, which in this case would be 12, into the shell over here. So we could do that, and that will work. Will it? Let's find out. And there we go. We've got some calculations, but and there's reasons that you'll do this we'll look into later. What you can do instead is you can put it in a variable. like this. I shouldn't be putting semicolons, that makes it more confusing. Let's not talk about semicolons. We could do it like this. So we could say, put this in a variable, which is what x is or what y is. You can have pretty much anything can be a variable. There's a few rules, but as long as it's... The one main rule that you'll fall into a lot is that you can't have it start with a number for some reason. There's probably some technical reason why you can't do that. It can't start with a number. Other than that, like as long you can even have numbers in it, just as long as it starts with a letter, it's fine. You can pretty much use any word. Oh, and there can't be spaces, so you can't have a variable like an apple. Like there can't be a space here. So you have two options. You can either underscore or you can capital letter like that. You get the idea. So we can put it in variables like this. But it's not immediately obvious why you do this, but I've got an example which I think is pretty good. That'll explain why you might do this. And this will give us the same output. So essentially, instead of just straight up printing it, we're saying put it in this area here, and then we'll print it out afterwards. And the two key things to know about variables is one, where they sit on the computer, and we'll talk about that right now as soon as I can find my 5-point model. So the first thing is where do variables sit, and second of all is that variables are temporary. So variables sit in RAM. The process is doing the stuff, but we can use RAM while programs are active. And they're temporary. Once the program ends, these variables disappear. So we temporarily put it in memory here, and then once the program ends, the variables are gone. Oh gosh, these are some serious questions. I'll try and read those in a bit. All right. Great. So that's that. Yeah, so why would you use variables? That's a good question. And there's like two answers we can really get to that. So the first answer is what if we're doing a really, really long calculation? So let's say our calculation was, and we want to print because we want output. Let's say it was plus 240 divided by this. I don't even know what this is doing, but like you get the idea. Like it's just a stupidly long calculation. As you can imagine, after a bit, it's going to start getting hard to read, especially if this has meaning. This doesn't, but you can imagine that it does. If it has meaning, then suddenly this is a problem. Whereas what you can do with variables is break it down. So we could say part 1 equals this, and then we'll split it here. And then part 2 equals all of this, part 1. And then we can continue the calculation there. We'll need to remove that parentheses, move that there, and then we can have it print out. And this will do the same thing as doing it on one line. So that's the first reason you might use variables. It allows you to split up long calculations. But there's also a second reason, which I'm pretty happy with. This is probably a bigger reason. So I'm not going to talk about this line of code because it's a problem to think about. But essentially what it does is, I'm not even going to talk about it, but we now have access to another function. We'll talk about functions more in a bit. But essentially here, let's say that we needed a program that printed a random number from 1 to 6. Wait, I need to stop putting it straight in there. Print random number 1 to 6. And then we say we need to print the random number. That's not what I thought was on the clipboard. Well, plus 1. But let's say we need it to be the same random number. I should probably draw a diagram here. Oh wait, let me see what the COC's question is. So can we store the code in the HDD, but where and for how long are the variables stored? No, because the variables only appear on runtime, is what I was saying. Yeah, no, yeah. We could talk about what's happening with variables more, but those are more data structures, and this is going to have a focus on algorithms over data structure. I probably should have said that, but the idea is you can't, as data structures are more important than algorithms, but you can't do anything with data structures until you have algorithms. So we're sort of talking about algorithms more first. All right, let me explain what's happening here, what I was trying to get at. So let's say we have a random number, we'll call A, which is from 1 to 6. And let's say the program needs to print out just A, but we also need A plus 1. If you don't do this without variables, so here we've got a program without variables, and you might just think, oh, we'll just generate the random number twice. Let's run this. Are we on program 3? I think there's going to be a lot of programs. What you'll see if we run this 1 or 2 times is here we got 6, 6. Here we got 6, 2. And you see, this isn't what we'd expect. We'd expect this number to always be 1 larger than the first number. This doesn't happen because we generate the number that's random twice, if that makes sense. So essentially, what we have to do to make this work Am I making a new shell? I'll make a new window. So many windows. Is to make this work, we essentially need to put a handle on the first round number so we can use it twice. So we need to have a variable here, just call it RNG or whatever. Put that in RNG, and then we can print out RNG, and then RNG plus 1. So I guess that sort of gives you an idea of the two main reasons why you'd use variables, and variables are really important. I knew I said I wouldn't spend too long talking about it, but I guess I end up talking quite a bit about it, but that's okay. So you can either use variables to split up long calculations, or you can use it to put a handle on a specific number. So in this case, the random number, we need one specific random number. We can't have any old random number for this algorithm to work, so we had to put a handle on the random number, in which case we called RNG. And as we can see, if we run this, it now works as it should. And we get outputs that we'd expect, where the second number is always one more than the first number. So variables in action, very cool. All right, let's do a calculation. Let's write our second program. Our first program was, is my first program gone? Oh wow, it is, because I use variables. Wait, I want my first program. I'm rewriting the first program. Just to summarize, the first program was 5 plus 7. I'll just put a second calculation. So this is our first program. Now we're going to write our second program. Program 1, true. Py. Alright, get that out of here. So we've done our first program. It didn't do anything, except it did do something, we just didn't see the output, and now we're talking about outputs. So let's come up with a calculation. Anyone got any ideas for calculations? I'd have to get so lucky. It would be unlucky though. In the end I got lucky and it proved the point I was trying to prove. Imagine if I had just got unlucky and it was just the same one over and over. Alright, let's write our second program. Any calculations anyone got idea for? What might you want to do? Let's just go like really nerdy and get something from chemistry or something. Alright, in chemistry we have PV equals nRT. Alright. What am I doing? And we'll use some variables in there too, because we know about variables now. We can add some spice. So we're going to have P is going to be equal to our answer, but we can just put any old value while we're waiting for the actual value. So put P equals 0. And then we're going to do a calculation. So let's do numerator for the bit on top of the fraction equals, what moles do we want? So we've got 0.1 moles. Oh, that's a constant actually. I should do this correctly. I hope it's for 8.31, hopefully. And then temperature. What temperature we want? Like 300. All right, and then we can have P equals numerator, which is a bit on top, divided by, oh, I should talk about operators. I completely forgot about operators. We'll do that in a second. Divided by volume. Let's say we got 2000. And we can print out P. So all we're doing, calculations, giving them handles, moving those values around with their handles, and then we're using an output here to see what the computer's doing, basically. And that is, let's run it. We now get a pressure, because that's what this chemistry equation does. And my computer just cannot compile code. The streaming's too much. Oh my goodness. There we go, 0.12, if anyone cared. And we can put a comment here. I haven't really talked about comments, but you don't need comments for a while. You kind of do. Okay, I should probably talk about comments. Comments just mean that you can write anything, and the computer won't try and run it as code. It's quite useful. It's a hashtag in Python. P equals numerator divided by 0. I don't need to. But the idea of programming isn't to write the fewest number of lines of code, and that's important. Like, for sometimes you do it as a challenge, but in general, the program is to show what you're thinking as well as working. You want it to work, and you also want it to show what you're thinking. I'm thinking the variable P should exist because that's our answer. So in my maths, I always put the answer exists. I don't know, it's just however you think. Yeah, it's not functional. We could get rid of this line, it would still work, but that's what you do. When you program, you write lots of relevant lines of code. You don't have to write every line of code to be relevant. And that's quite a useful programming construct. Is sometimes you can add irrelevant code to make it clearer what the program does. It's good practice. All right. We have done a sequence program with the output and with variables. Very good. Let's talk about operators quickly, I guess. All right, operators, arithmetic operators. Oh wait, no, I should put start basic, no, not basic, start arithmetic. Oh gosh. How's that going to look when I print it out? It's going to look acceptable. So I guess just to begin with, the 4 operators we'll talk about to begin with is times, add, minus, divide. And you'll need some other ones later, but for now that's easily enough. And you can sort of, these ones we both know, these are just as you'd expect. What symbol I put for as you expect? Let's put a tick. You understand addition and subtraction. This is what we use for divide. I probably should have done this at the very beginning. I did not think about this, but hopefully you got the idea. And this is multiply. Yay. Okay, right, now we got that out of the way. This is going to happen a lot, by the way, because essentially there's all sorts going on at once. So I thought, just go through the structure, but if there's other things, I'll just dump it in the extra section and we'll look at it quickly. All right, we've done the second of 7. I'm doing all right for time somehow. There's so much here, oh my gosh. Oh, I really needed a beginner programmer viewer so I could tell if this is making any sense or not, but it's okay. I'll just keep pushing forwards and hope for the best. All right, we've done it. We've done an output with variables. That's essentially what this is. And now we're going to look at input. So, how do I explain input? How do we go into input? It's a good question. So, let's write another example program. This one's going to be a lot more like you can understand why you might want a program that does this. With this one, it's kind of like not many people are chemists, but a lot of people can get this one, so that's good. So we're going to say R equals, in this case, is our input. No, that'll be confusing. So all we're doing is we're saying 5.4 exists. Like, you can do this. A calculation is just 5.4 exists. Doesn't look like a calculation, but computer sort of treats it as one. You're just saying 5.4 is there. We're giving it the name R. All right, and then we're going to do a common calculation people are probably very aware of. We're going to do, can't do pi doesn't exist. We're going to do pi times r, pi r squared, which is the area of the circle. And then we're going to print out the area. Very good. And what does this do? It gives us the area of the circle with a radius 5.4. Wait, how's my lighting? I just realized. Oh, my lighting's fine. Sorry, I just realized because it's getting dark, so when it gets dark I have to use some artificial lighting, but it's all good. So people are aware of the area of a circle. Let me get some water. But as I mentioned previously, oh gosh, so many pages. Oh, it's here, isn't it? We're going to have a focus on mathematics, and within mathematics, a common practice and a really good practice is once you've solved a problem, and here the problem was, what is the area? Oh gosh. In this case, the problem was, what's the area of a circle with radius 5.4? Oh, we should show that it works. P1.py. Show that it works. We're asking here, what's the area of a circle with radius 5.4? I should get a calculator so I can check it. There's my calculator over there. Oh. It is 91.56, and we can check that too. 5.4 times 5.4 times 3.14. Yeah, my calculator got the same thing, 91.56. I don't know if you can see my calculator. If not, that's fine. But you get the idea. The problem works. We found out the area of a circle with radius 5.4 units, and then we got an area also in the same units. But as a mathematician, you don't just want to solve the problem for one case. This is only one circle with radius 5.4. I'll show you what I mean. So we've done it for a circle. Wow, that's an interesting circle. With radius 5.4 units, right? But as a mathematician, you don't want to just find the area of a circle with 5.4. You want to find the area of any circle with a general radius r, which could be bigger or smaller depending on what r is. So we can actually represent the idea in programming, and this is a really important stepping stone to make really meaningful programs versus just it does a calculation and stops. is a, where is it? Oh wait, I'm writing code, aren't I? Right. So what we can do to represent that idea is here where we put r equals 5.4, we can say r equals, and here's the really exciting bit, we can do this. All right, let me write it, and then I'll run the program, and then I'll talk about what just happened. And this is our third program. Oh gosh, that already exists. Program 3 true. All right, and then when we run the program, you'll see we don't just get a number thrown at us. Oh, it's taking so long to compile, what the heck? I have like no memory left. Huh? Oh, I know what I did wrong. I know what I did wrong. It's my coding. My bad. There we go. So now we don't just have a number at us, we have a thing which is meant to indicate inputting. You can make it fancy, you can do whatever you want. Like here you can put input if you want. Whatever you want to make the user know that they want to input. And then we input. So let's say we want, oh no, that's a mistake. 1 sec. That is a mistake. So then if we input, let's say this time specifically we want 0.3, that will tell us the area of a circle with 0.3 radius. Or if we wanted 12.9, that'll give you the area of a circle with 12.9 radius. So now you can see, as like in maths, you generalize it. Only not only is it generalized, it's actually useful. We can use this to find the area of any circle with any radius. So what's happening here? It's a good question. We could talk about this in terms of functions. Gosh, functions are so fundamental. I didn't realize this. But it's just I wanted to get some other things down before functions, but maybe we should do functions first. I'll keep that in mind if I do this again. Essentially what input is it's a function. We haven't really looked at functions yet, but essentially this all becomes a value, whatever the user types in. But the problem is the computer doesn't know, are you typing in a number or are you not typing in a number? So for example, if I type in cake, that's not a number. So this is a string because we don't know. Oh, we haven't spoken about strings. Oh gosh. We can do that in a bit, but essentially it will come out as a string. What a string is, it's just anything. So cake is a string as opposed to a number. Cake, but also numbers are strings as well. So a string is just any sequence of typable characters is what it is, and that's quite important, so I might just write it on here. Sequence of typable characters. Is it spelled wrong? I don't care. There we go. That's a string. But obviously we don't want a string, we want a number. So what we do is we use what's called casting and we turn it into a number. There are different types of cast. You can do, the two ones for numbers in Python are floats and ints, but different programming languages have different casting. Essentially for now this is just a single unit, as this is how you input a number. It's this code. And then here this can be anything you want, and you put it in quotes to say it can be anything you want. Haha, input number go. There we go. I was thinking about this for a while. I was like, this is really hard to communicate. I'm realizing just how hard it is to just go straight at programming, giving it a bash anyway. So now it works as usual. So you can put literally anything in this argument here. In this case, we're putting a variable, and we've spoken about variables, so we can put our text up here, put it in a variable, then use that variable. Great. There we go. Fantastic. And there we have it. Areas of circles. I think we've pretty much covered everything that can be covered here. I think we can move on. I would say any questions, but the people watching my stream, or at least 2 of them I know, actually don't know who's watching my stream. If anyone's got any questions, if nothing made sense, please do ask. If not, I'll continue onwards. Alright, so we've now done input. That was quicker than I thought. I did input of numbers. But input of numbers is pretty much what we're focusing on. We're focusing on mathematics. Really, we could go into input of anything, but I should probably put that in brackets, just input of numbers. And I'll put the syntax for that too. The input of numbers is variable name variable name, or var name, variable name for short, equals float, input, input. 1, 2, yeah. That's our code. And where input's a variable, which is a string. Should probably put that too. We use the symbol str for string, in Python at least. I don't know about other languages or other computer scientists. Okay, I think we're done there. I think we can move on just about. All right, fixed iteration. Oh, this is fun. This is very fun. This is where programming gets fun. Oh, I won't still be streaming in 45 minutes, KSU. Rip complex numbers. Bro, we're not going into complex numbers now. 45 minutes? Yeah, I won't be streaming then. The stream's going for like another till 7:15, so that's 20 plus 50, 35 minutes. So yeah, I won't be streaming then. See you, KSU. All right. We can move on to the really exciting stuff now. We've got sort of the basics down. We know how to input numbers. We know how to put things in variables, do some calculations with the 4 operators we looked at, plus, minus, times, divide. Let's do some iteration. And there's 2 types of iteration. We're looking at the second type later, but for now we're looking at fixed iteration. So I'll give the example now, and then we can look at what's happening later. All right. Oh, I should have made an incrementable. I might make that quickly as I do it. All right. So let's say, right, so far we've got a pretty convincing program that lets us, this is a constant at the top, that lets us input a radius, and then it will calculate the area and print out the area. It's a pretty useful program. Let's say we had 7 circles, say, all with different radiuses, and we wanted to find the area of all of them. What we could do is we could do some fixed iteration. So let's look at that. That is the syntax. So this is just a syntax which, again, like with the input, you just sort of, you learn it over time. You can look at more in depth what's happening, and maybe I'll do that in later videos, but for now it's just syntax that you write down or whatever and just know what it is. This can be any variable name, by the way. We won't go into this later, but this could actually be anything, but just keep it as I for now. And this number here is the important one. That's how many times we're going to repeat. So here we've got 7, so this is going to repeat 7 times. I don't want to comment there. Right, now I want an incrementable. How long will that take me to code? It's a good question. No, I'll be fine. I think it won't take me too long, so I'll just go for it. That's the worst code you'll ever see, but it's all good. All right, so we're going to have an incrementable. We're not going to be talking about what this is, but it's fantasy is what it is. Let's call this something easier to deal with. In fact, actually, if I do my next part, the object-oriented one, we'll actually talk about this more. All right, so starting with 0, the incrementable. I also talk a bit about what's happening with this. Dot increment dot dereference, print increment dot reference. So essentially what's happening here is we're saying start at 0, and then each time the incrementable is going up 1 incrementing. But we don't need to go into that too much. This is just so we can keep track of how many times it's looped. All right. Which one are we on? Oh gosh, where is it? We've done that one. Part 4, program for troop to py. Let's see what happens. Hopefully there's no syntax errors, because that would be no fun. Wait, so that's the first iteration, so we can do like 54. Second iteration, maybe the next circle's 20, next circle's got a radius of 2, next cycle's got a radius of 0.4, and you get the idea. So you can just keep going through like that. And so what happens is it did the same program 7 times because we told it to do it 7 times. And we can sort of ignore this as just technical stuff. Ignore. What essentially is happening here, and we can ignore all this too, but you sort of got the impression with that. we're repeating 7 times this program here of you get a number and then you calculate the area and then you print out the area. And that's quite useful sometimes because the alternative to doing this would just be to get this and to just print it out. Oh gosh, why is it doing that? Print it out 7 times, right? And that's no fun for anyone. How many times is that? 1, 2, 3, 4, 5, 6, 7. And no one wants to be doing that. So fixed iteration just allows you to save time on writing code. If something does the same thing over and over, you don't have to write it out, you can just tell it to repeat. Okay, I think that's done. That one's not too bad. There's some hard stuff coming up though. This is already hard, but there's some harder things. Oh gosh. Give it a jab. Alright. Fixed iteration, we get the idea of fixed iteration. And the syntax, maybe I can do a document that has like all the syntax you need from this. You want to start writing code. And the idea is we're just looking through some examples. You can mix and match all the things in different ways. That's what programming's all about, really. Alright, selection. What is selection? What a question. And also I put here that a Boolean logic / algebra is a prerequisite. Yeah, it really is. Neither's fun. Oh gosh. Alright, how do I want to do this? How my viewers have gone sad times. Okay, let's give it a bash. Right, I spoke about this in a previous video. It's not a prerequisite though, so I guess I've got to go over it again. So, I've spoken about variables. We can have some variables. In Boolean algebra, which is what we're looking at, Boolean logic / algebra, I'll call it Boolean logic because that'll be easier to think about. Boolean logic is essentially like algebra with 5 plus 4 or 7 plus 8, but you have different values and different operators. So in decimal, you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Right? But in Boolean algebra, we only have true and false, and that's it. And the way as the final values, you can do different operations, but those are the final values. And the different operations are, you can do, I want to do some logic up here. Oh gosh, I'm running out of time. Functions are really important. We need to get to them. I guess I'll have to just... Set up a data structure. 1, false, 2, true. Lookup, random, 1, 2. So essentially we're setting up 2 general Boolean values here. Alright, and the different operators are and. I spoke about this in another video, but that wasn't a prerequisite, so I guess I have to do it now. But it's okay, because Boolean logic's actually not too big of a topic. Well, it is if we looked at everything fully, but we're not going to. So these are the 3 different operators. So you got and, you got or, and you've got not. Okay, and the way it works is that because there's only 2 values, true and false, these will always evaluate to just true or just false. It'll be one of the 2. So in this case, if both bool1 and bool2 are both the value true, then that operator will cause this whole variable 1, all of this, to be true if both of them are true. Let's do a drawing. Let's do a drawing. I ran out of space here. Yeah, let's do a new one. It's okay, it's not wasting paper because it's digital. Alright, let me write this out. Make it nice and big. Nice. So essentially, if they're both true, yeah, we can do this. I'll put it out a second time just in case I want another example. I'll put a few examples just in case. So essentially, if they're both true, oh gosh, come on, computer. if they're both true, then the output is also true. And if there's one true, one false, I guess I can do it on the next one. Then because it's not true and true, which gives true, it'll be false. So any other combination, and there's 4 different combinations. So if we think about true as being 1 and false as being 0, oh gosh. Then we can figure out that all the combinations are 1, 1, 1, 0, 0, 1, 0, 0. So this combination 1, 1 gives true, and all the others give false. Hopefully that roughly gives you that. But I might make another. I have to make a bunch of documents on this, I guess, just to cover all the syntax and technical things. Okay, so with true, if they're both true, true, otherwise false. Oh, I could do it as a truth table. Let's do it as that. Truth tables are much better. You can summarize a lot of information a lot quicker with it. These are the 4 combinations, right? And essentially you can just give the outcome for each one, and it will give you all the information you need. So let's just do that. So this is and. Oh, I should have just given a rough outline. I just wanted to give an example. I wanted to give like concrete example, but I guess it would be better to just talk about roughly how it works. Oh well. And this is all. And then not. Let's do not right here. For not, you only have 1 input, so if it's 1, you get 0, and if it's 0, you get 1. Oh, I have to remember my webcam's in the corner. Oh no, I hope it hasn't gone underneath my webcam. No. This is hard. I knew it was going to be hard, but I thought I'd give it a bash. Okay, selection. Maybe I should just jump. Oh, let's look at this. This will be cool, I think. All right, this is going to be cool. Boolean Logic.py. And if you want any of these resources, just like say in the comments, I'll try and distribute out as much of this as anyone wants or doesn't want. If that would help. Oh, what? Oh, okay. I'm just going to have to print them out one by one. There's no quick way to do that. It's all right. It'll take 2 seconds. So now we can see what happens when we put in 2. So these are both randomly generated. So we got false and a true. And so here we got false and true, because this is going in as bool 1, this is going as bool 2. And we've got true and false. Only one of they both need to be true for true, but then one of them's false, so it gives false. Then we got or, which is basically asking is this or this true. In this case, this one's true, so the whole thing's true. And then we're saying not bool 1. Bool 1's false, so not of that is true. Okay, that was a crash course in Boolean logic. And now let's look at some example code. Oh, I wanted to basically, right, okay, let me find it. In my head it would be like, oh yeah, look, here, selection gets used because we've got elif. Elif is else if, but it's basically just if. If is what selection is basically saying if this, do this. But this isn't really the best example ever. Let's just do some code. Basically, selection's like super specific. Like, it's quite slow. This doesn't really concern you much to begin with programming, but eventually later on you want to avoid using selection. So think of it as like a specialist thing. Sometimes you'll need to do it, but other times you won't. Let's just do a simple program. Let's put choice equals yeah, we haven't spoken about int, but it's okay. You'll have to get into int very quickly. I might have to do a video on casting because there's more to it than I remembered. Let's clear that. Dump that in there. what do we want here? We want a monkey here. It's going to be such a mess. Let's do this. We need these two to be related. No, we don't. Yeah, we can do that. It's so specialist. I can't think of a good simple example because, like, sometimes basically selections, you have your algorithm that does various things, and if you need to force it to go one way or another, you can use selection, but a lot of the time you can just logic all the way and you don't need selection, but I guess you do. You'll need it here and there. Alright, what does this program do? It's a great question. Essentially what it does is that it's testing these two. So I looked at and or not, which are like the main ones theoretically, but on a practical I forgot about these. There's more operators. These ones are actually easier too. I don't know why I went into and or not. I guess because they're more theoretically important, but practically not really. Oh no. So if we put 2 on both, it skips the code print monkey because choice 1 and choice 2 are both not equal. Neither of them are equal to 1, so we skip the code. Whereas if one of them or both of them are 1, it will do it appropriately. So if it's 1, say 5, we'll get the monkey but not the cake. Or if it's both 1. I know this is the lamest example ever, but like using selection, finding good examples. And you can chain it with elif, but that's so complex. I need to do a whole video on selection, I guess. But that just gets... It's just where it gets chaotic. Yeah, we could look at this, but like, oh gosh. Alright. I should probably talk about equals and not equals. Let's do that. There are actually, like, I'll put all of them and then we'll look at some of them. I forgot about these because I'm silly. I probably need a new slide. So in all we have, oh gosh, as well as and or not. So we got and or not. I'm running out of time rapidly. I only have 15 minutes left. I need to go quicker. As well as and or not, we have equal equals, not equals. This is just equal to. It's read equal to, but it's important to think equal equals because you don't want to get confused with just one because that does something completely different. Bigger than, smaller than, bigger than or equal to, smaller than or equal to. All the different ones. But of all of them, the ones we're going to look at now are just equal to, not equal to, bigger than. And this sort of applies to smaller than too, and roughly to these, but a bit differently. Equals to, if they're both the same, it's true, otherwise false. So I can just write an example. So 1 equals 1, true. But otherwise, if it's like 5 equals 14, it'll be like false. And then not equal to, it's the other way. You get the idea. So if it's 1 not equal to 1, that's false because 1 is equal to 1. And then 5 not equal to 14, that's true because it is. And then bigger than, it's just as you'd expect, like 14 bigger than 5, 14 is bigger than 5, so that's true. Or if it's 3 bigger than 20, that's like false because 3 is clearly not bigger than 20. Okay, gosh, there's so much covered. Great, let's go back to the contents. We've looked at an example of selection, realised that selection is a pain and needs its own video. Look at conditional iteration. Conditional iteration is better than selection. I can do that quickly. Oh, and then we're nearly there. Nearly there. Oh my gosh, just programs, subprograms. This one's actually fun. Some of this is just dense, but you have to get through. And this will give you a rough idea on how to approach these topics, but I guess you'll have to do a bit more before you can get proficient in programming with them and stuff. this, I think it's been an okay summary of what's going on in programming. Look at conditional iteration. Okay, if you say so, my previous self notes. Right. I guess the most common example of this, and the reason why it's a common example is because it's so useful. We haven't looked at collections. That's something I should add to my. We're going to need collections, so let's dump it on the list first of all. We're going to look at collections, which is a list. All right. Oh, and it's going to tie into Boolean logic. Everyone's favorite Boolean logic. The problem with Boolean logic is you need it to do computer science and computer programming. It's just so difficult to communicate and not very fun. I might need extra lighting at this point. There we go. Extra lighting incoming. Okay. So let's create a collection, or otherwise a list. And in Python we call it a list, just different types of collections. But lists are pretty useful, especially in Python and other languages too. Some programming languages call them arrays though. Some people call them arrays. Python we call them a list, and a list you'll be understood, so we'll call it a list. I don't know if I want to call it a collection or a list. I'll call it a list. It's called a list, but you can think it's a collection. A list is a type of collection. I need to draw a diagram for that, don't I? Oh gosh. So it's like these are collections. And then within collections, we have lists. So you also have some other ones that aren't in here. Wait, let me show you. It's like a subset. So all lists are collections, but not all collections are lists, because you have tuples also, and also you have all sorts of things. Like there's so many. I'm not even going to go into all the different collections. This is all data structure stuff, which like you can learn about this stuff more easily than algorithms. I don't think there's anywhere good to learn about algorithms. Learning about algorithms is a pain. Okay, but I'm going to be calling it a list from now on because that's clearer and a better idea than calling it a collection. Even though in my head I want to call it a collection, it's a list. So, okay, so those are options in a list, 1, 2, 3. And essentially what you might have is while, let's call it user input, while user input, while not, we looked at not, user input in, so while it's not in options, and this is another expression, we didn't look at in, but essentially we're saying, what in does is you have a value and you have a list, and it says, is it in the list? So it'll look at each item in the list, see if it's in there or not. I mean, you always do lists with squares, that's important, square brackets. I'll put that because that's like, you can remember that. You put it in square brackets, it's just something you have to commit to memory, unfortunately. There's no way to know why that is, it just is. User input equals none. Yeah. Equals integer input. We've looked at inputs, looked at how integer sometimes you want to use, but I didn't really clarify. If you want just numbers though, you use float. But here we want a very specific type of number, we want an integer. I kind of explained it really. Int for integer, or just a number in general, float. But here we specifically need it to be an integer so we can compare it to other integers. Alright, input equals, boop, like that. Oh gosh, 11 minutes left. Is this going to work? I think we did it. This is called a validation script. You don't need that to know that at all. But it is. But what it also is an example of where you might want to use conditional iteration. Conditional iteration, I should probably say roughly what it is before just programming. I'll do that in a second. So if we type 4, it's like, no, that's not in our list. But if it's 3, it's in the list. So it says you chose 3. So what does it do? It keeps repeating this code as you saw. It repeats it over and over again until this condition is true. And that's like all of what conditional iteration is. So I'll put that on a slide because that's big. All right. So conditional iteration is characterized by repeating forever. If true, continue. If false, stop. So here, where is it? Where is it? Oh gosh, so many programs. I should close the programs as I continue, but I didn't because I'm silly. So here we're saying if it's not in there, so not in there, so if it's not in there, it's true. Because we're asking, is it not in there? Boolean logic, man. So if it's 4, if it's nothing, as we've got here, then this would be true because it's not in the list. So essentially, if it's 4, 5, 18, whatever, it continues to be false because it's not there. But as soon as it is there, it becomes true. No. Well, it's not in there, it's true. Oh gosh. Well, it's not in there, like if it's 18, 9, 22, then this is true because it's not in there. But then as soon as you have something that isn't there, so if you have 1, this suddenly becomes false because 1 is in there, and then it breaks out and it runs this. That was actually, I was able to explain it much better than selection. Selection, dearie me, so much harder than I thought. I knew it was hard, but I didn't realize just how hard. There we go. You have a rough idea what's happening there. Oh my goodness. This is such an adventure. Am I out of water? What a disaster. Oh man, I didn't bring enough water. I just don't want to risk it. I'm thirsty. Okay, great. We've looked at all 6, final one left, and I've got 8 minutes left to do it in. I can do that. Great, so far we've looked at the structure of algorithms. How do you make the computer know what to do next? If you don't get anything else from the video, that's like the one takeaway that I can give you. Algorithm. Making the computer know what to do when. Nice. No. Okay, and we do that through these 6 parts. And these 6 parts make up like a complete thing. This 7th part you don't need, but it's really important, so we're going to look at it for this last bit. How can we do it? We can just tell it things to do. We looked at that here and here, one with outputs, one without outputs. The first part, we just make it do a bunch of things, no outputs. Second part, we make it do a bunch of things, but we have outputs. So those are 2 things you can do. First one's not particularly useful, it's more for demonstration purposes. Then for free, we looked at how if we have inputs, then we can make input and output, and we can make more meaningful, useful programs, but still doing things in order. And then here, this is the control flow section. It's what programmers tend to call control flow. And the 3 different types of control flow, and this is quite important, I'll put on another slide in a second, is fixed iteration. It's just, you have a piece of code, repeats it a fixed number of times, so repeat it 7 times. Selection, where you're like using Boolean logic complicatedness to decide which way to go. And then conditional iteration, repeating forever, but you have something that will stop the foreverness from happening. So if you don't take anything else, then at least there's that. Looking at what these are, fixed iteration, selection, conditional iteration. I can do a diagram for each. So let's do a diagram for each. This is called control flow. Fixed iteration, and a diagram for that is repeat 5, for example. All right, and then we got selection. And you can think about selection as choosing which path. So we could imagine, like, you know about graphs, thank goodness. So it could be like choosing which way to go from a given point to the next point. That's what selection is. And you can only go one way. So it's like, which one do we go? Put like a question mark to show which way. That's selection. Oh, and it heavily relates to Boolean logic. Like, it's fundamentally associated with Boolean logic. Both of these 2 end ones are. Fixed iteration isn't, which is why I was able to communicate it reasonably well, I think. But these 2 do, and Boolean logic's big, so probably why I suffered trying to explain it. Oh, that did not work. Oh, that did not work. Okay, and what is it? It's repeating ever, but you have something to make it stop. Is that going to fit? Everything except but. Okay. I only have 5 minutes for functions. No, functions are cool. I wanted to fit everything in this stream. Now something doesn't fit. What a scam. Have something. That's going to put something on its own, but I don't really care. Now it looks like I'm writing poetry. That's okay. Splice it down there. Repeating forever, you have something to make it stop. And again, unfortunately, it ties into Boolean logic. You need Boolean logic. I need a video on Boolean logic. I didn't realize just how important Boolean logic was to programming. Turns out, very important. Oops, big mistake. All right, but there's something here, and I can send out this thing, so you can download it or whatever if you want it. So fixed iteration, how many times do you want to repeat this section of code? Boolean logic, selection, which way do you want to go? Requires Boolean logic. Conditional iteration, repeating forever, but you have something to make it stop. Again, related to Boolean logic. Great. Now we can tackle the final hurdle of this epic marathon. Oh my gosh. Programs, subprograms, functions, procedures, all that fun stuff, but this is okay. I like this stuff. Oh my gosh, how many different slides. You know what, I should probably just, can I just force quit Python? Let's do that. Just tell my Mac to just force quit Python, and then it'll all be good. We can have a fresh start. As long as it doesn't try and reboot everything, that would be disastrous. Please, I want a fresh, clean slate. I've made a mess. Oh, but I might want some example code. Oh well, I can type some new example code. Right, let's do this rapidly, because I'm running out of time. Example code, example code, example code. R equals floats, input, area equal, oh this is great, this was fast. 3.14 is pi times r, print area. Whoa, that was pretty good. Okay, so let's say you have a program like this that does some stuff. All right, this is the bit on a subprogram. So what is a program? This is a program. This whole thing is a program, and what it does is the input is we start the program. It might have various inputs in it, but fundamentally it's an input is that we start the program. That's an important part of subprograms, and then it outputs something. And so long as it also must have a name. Those are the three important things of a program. It has a name, it has inputs, has outputs, and the inputs don't have to be any specific inputs. Just starting the program counts as an input. Epic program 1. Wow. So now it has a name. So essentially what we can do is Python actually lets us emulate the whole program within the program. We call that a subprogram. So what we could do is within this, what we could do is a slightly different program. Let's have another program. Let's call it circumference. So in the same way where you save the file to put a name for the whole program, you can just write the name like this. It's pretty fun. I don't know how to spell circumference. It doesn't matter. I can put whatever I want. I'm a programmer. Circle mood. No, we're not going to that yet. So you can say define just means we're writing a new program within the program, a subprogram, and then we can do something like that. So maybe r equals floats inputs, input, and then put c for circumference equals, and that's 3.14 times r times 2. And then what we can do here, you could just print it, but you can return it. We'll look at that in a second. And this whole thing could technically return, but it can't for some reason. But imagine it could, but it can't. But imagine that the wider one could, because that'll make it easier to think about. All right. Essentially now we've got a program within the program, a subprogram, and we can classify subprograms differently depending on how they work, what they do. So this one here is what we call, like, I guess like the intentional output, or we call it like the return case or return value. If it has a return value, then it's a function. Otherwise, it's a procedure. So we can actually make a procedure version of this. If it just printed C instead, now it's a procedure because it doesn't return anything. And essentially, anytime you have an input that isn't just returning, it's called a side effect. And that's really important. I wanted to talk about side effects. So this is a side effect. So because it doesn't go through return, this is a side effect. Why do we call it a side effect? Well, I'll show you why we call it a side effect. This is so much better than the other content. I should have moved to this sooner, but I was too busy caught up on the other stuff. Right, if I do... Why am I doing age? Value equals circle mood. Oh heck, we don't need to use a variable here. Whatever, we've learned about variables. We deserve to use them. Not deserve to use them, we've earned using them. I don't know what I'm saying anymore. So let's say we're just trying to use our circle mood program. We want to know the circumference of a circle with unit 3. Oh, this is the first one. Oops. We can comment it out. We know about comments. Wow. Epic gamer. Don't want to deal with that. 3 units. Right? What we wanted is this. But hold on a second. Hello, where did that come from? It's a side effect. So side effects happen when because you see, we use it by, when it's returned, we can use it in that when we call the function, we call that calling the function. When you push the run button, this is essentially, when I click the run button, it essentially does. Epic program 1 is what it does when I push the run button, but we don't see it. So we can essentially push the run button on this mini program, this subprogram, by doing that, like we do that. And this is just the syntax for it. You can't really explain why, it's just, that's how it is. Sometimes it'd be like that when you're coding, implementing your programming ideas. So essentially we can, this becomes its value. So it returns C, so it becomes C. So value becomes C, and then we can print out C, which in this case 18.84. So that's what we expected. We expected this. This isn't a side effect, we expected it. But we had a side effect happen as well, which is pretty fun. Talking to side effects more, essentially the problem with side effects is that because you don't know what's going to happen, it can cause problems when you have too many side effects in your programs you're not aware. So that's just a fun programming thing to talk about and think about. Is that all I wanted to cover for this? I hope so. Oh my gosh. Program, subprogram. I want to go back to my original. Oh no, please don't tell me I closed it. I did. I am so very silly, is what I am. This is not good. Preface slide. Excellent. I did a preface video because I needed a stream, because I was doing a daily stream thing. So I think I've covered, I just want to make sure I've covered everything I said I would. Oh, why data structure are often better than selection. Oh gosh. That's a good topic. Have I got time? I might have to do that. Functions, procedures, we talked about the difference. Function side effects, talk about the need for function side effects. I guess I have to cover that. Let me do it purple, just so I remember. Okay, and we also need to look at data structures better than selection. They're good topics. I should have had this open rather than my contents page. This is much better. Need for function side effects. Essentially, the problem with the return value is you can't do anything with the return value, right? And so essentially, without the side effect, if the whole program, wait, let's do this, didn't have any side effects, we can comment out mass things using a hotkey. I'm not going to go into that. If our program didn't do anything but some calculations, 5 plus 5, return 5, and then remember we said to run the program, we just do that. If that was our program, like as we saw this was our very first example, nothing happens. And there's no way to do, say, print with the return. The return has to just give a value. So if there's no side effects, your program will do nothing. So essentially the philosophy is that you need side effects. So even though side effects are annoying a lot of the time, like fundamentally you need the side effects, because the side effects are what are going to make things happen. So in this program, even though it doesn't seem like it, this whole thing's a function, the whole thing's a program, this print value is actually a side effect. If we wanted to have it do its thing properly, you can't actually do this, but like imagine you could, it would do that. It would return the value, but we're printing it, that's a side effect. So essentially you need side effects. If that didn't quite make sense, sorry, maybe I'll have to make another video following up. Just wanted to make sure I did everything I said I was going to try and do in the preface. So I've done that. Need for side effects. Because if you just return a value, nothing happens. Something needs to happen other than just giving a number for the program to do anything. So hence we need side effects. Why data structures are often better than selection? What a question. Okay, I can write an example program that explains that. And then I'll end the stream. Oh, I want to do a summary. There's too much to summarize. Basically, the conclusion is I tried to fit too much into one stream and I didn't have enough time to do it. Excellent. Hey, I gave it a bash. It's all good. All right. So let's say I need my random. Why didn't I shouldn't have closed all the programs, but it was a mess to sort through. So maybe this was a good idea. Lookup equals. I need to hide this away because it will confuse everything if you can see this code. Let's pretend you can't see this code. Okay. And this falls into data structures, this thing here, and we're not talking about data structures. That's not part of the scope of this. All right, and then let's hide the program. Let's go a million miles down so we don't see it because that will confuse the heck out of this next bit. Okay, so Boolean 1 exists. How does it exist? It's from another program up there that we're not going to look at, but essentially it's going to be randomly either true or false. Okay. No, it's not. Oh, I've messed everything up. We live to learn. But we're still going to hide that code because it's confusing. All right, so this is going to be a random integer. I'm going to use a comment here. Random integer 1 or 2, right? And essentially we need a program where if it's 1, it's going to, instead of having a 1 in Boolean, we're going to have, so I have a 1 in Boolean, we're going to have true. So the program rules are, you can call them program rules, outcomes, criteria, whatever you want to call it. 1 should be true, and 2 should be false. Okay? Let's look at the first way we could do it. We could use selection. We've looked at selection, like very crash course quickly, but you got the idea, hopefully. So if bool1 equals 1, bool1 equals true, bool1 equals 2, bool1 equals false, print bool1 just to show this is a side effect, remember, just to make sure that it worked. Like the program still does its thing even without this. It's just we don't see it does its thing. And that's essentially the idea of programming in terms of side effects and functions, which is one of my favorite topics. I should have just done a whole video on that. Data structures pog. That's what this program's going to be called. All right, run it, and this will work. Oh, we need to know what the number is. Just see, side effects are everything, but they're also really annoying. They're everything and annoying. That is side effects in a nutshell. So bool1's 1, so it's true. Or if it was 2, I can't control when it's 2, so I just have to keep running till it's 2. If it's 2, it's false. All right, so this works. So this is a selection way of doing it. But now what we're going to do is we're going to, let's put this inside a function. We know about functions now, just about. We can define it. This is why you'd use functions. We haven't talked about this too much, but you can move algorithms around as if they're a piece of data, even though they're an algorithm. Very cool. Functions are awesome. Should just do a video on functions, maybe. Maybe that's the future, do a video on functions. That'd be fun. All right. Let's call this program 1. We can essentially encapsulate our entire program 1 in here. So we can write a second program, and now it won't run unless we call the program. So we can have this code sitting here. This is an alternate way to do comments, basically. You shove it in a function that you never call. Pretty sick. All right, let's copy paste it. And you can copy, it's just functions are amazing. You can organize things amazingly. And organizing is like actually functional in programming. Unlike in the real world, where if your room's a mess, it really doesn't matter. In programming, your code cannot be a mess. That will actually cause problems. So you got to be organized in programming. It's very important. I say, well, it's a mess. This is pretty organized. It's organized. Okay. Program 2. Essentially, this is the data structures way. We haven't really spoke about data structures too much, but let's just show you a data structure. We'll call it Jeff the data structure. So why not? This is a dictionary. What dictionaries do is that they say you can assign things to a thing. That was a terrible explanation, but we'll do a better one in a bit. And essentially, just to show what this does, we should have program 2 called over here. If we print out Jeff 1, so we're saying at data structure Jeff go to 1, that will print out. Come on, computer. Oh no. Oh no, it's not global. Let's make it a global variable. Don't ever do this, kids. But you shouldn't use global variables, but we're in a rush. And that'll work. Oh, ignore this too. No, I need to make it clear. I'll call it Jeff so me, you can know it's Jeff. And you see, as you can see, Jeff is true. So what is Jeff at 1? It's true. And as you can imagine, also if we say what's Jeff at 2, well, we've defined it in our data structure. Jeff at 2 is false. And if you're quick, you can already see how we can ditch selection using our data structure. If you're not, I'll show you the solution. Essentially, we can ditch selection. If you can ditch selection, do it. So what we can do is say bool1 equals Jeff bool1. So we're saying we want bool1, our new value of bool1 to be at Jeff at bool1. Bool1's going to be a random number of 1 or 2. Random 1 or 2. So if it's 1, we'll put it into Jeff and we'll get out true. If it's 2, we'll put it into Jeff and we'll get out false, and it will give you the correct value of bool1. And you see no selection, and no selection equals faster programs, better programs, everyone happy. Like sometimes you have to use selection. If you have to use it, use it. But sometimes you can ditch selection. In this case, we can just get selection out of it, which is nice because no one likes selection, except people who do. But I get the impression people don't like selection. I don't like selection. Switch statements are cooler, but we don't have switch statements in Python, and it's very sad. So there we go. So when we got 2 false, we can do a few more test runs. When we got still 2 false, I want a 1. Give me a 1, please. 1, true. There we have it. We managed to use the data structure Jeff to avoid any sign of selection. Nice. We have now covered everything on the preface. I didn't lie to my viewers about what the video would contain. Let's go. Poggers. We did it. We did it, guys. The estimate was 1 hour 30. Not a bad estimate. I just started too soon to another event happening, and I'm going to have to dash for that in a second. Alright. We have covered that pretty convincingly, I would say. Summary. Side effects will make a program happen. You can do programs without side effects, as we saw here, but then it does a thing and no one knows it does a thing. No one cares. If like something happens, you don't ever see it happening. Might as well not have happened, right? So we need side effects, which is what this section's about. And as far as this section's concerned, we're looking at input, output, sequence, variables. It's actually hard to summarize that stuff. You'll do it enough and you'll start to get a grasp for it. But you can't really just like, I thought you could, I guess you can't. You sort of just have to work at it until it makes sense. These bits here, control flow, you actually can, and I did a summary slide for that. So I'll just have a quick look at that and then we'll end the stream. Wow, this is a marathon. And this is that. Fixed iteration, repeat, fixed number of times. Selection, which way do you want to go? Related to Boolean logic. Conditional iteration, repeat forever, but you have something to make it stop. Also connected to Boolean logic. And we saw that we could use that to make sure we have a certain input within a range. So for example, we wanted the input to be 1, 2, or 3. So it repeated forever until they typed 1, 2, or 3, and then we made it stop using Boolean logic. Okay, finished. Hope you got something out of that. I don't know if you did or not. It was chaos. I tried to plan too much into one thing. It's kind of fun. Maybe you got something out of it. I'd love to know. Like, honestly, I have no idea. Is this completely useless? Did you get something out of it? Is there any things that like just need clarifying? The rest would all be good? Let me know in the comments, and I'll maybe try and work on some documents if people want. If not, I might do it anyway, just of some image files or whatever that help clearing up some of the syntax here if people want to have a go at Python using some of the ideas I put forward here. All right, I have a Discord server too. It's cut.ly/ceo-discord. It's in the description, but you can join there. You can have a talk about these things if you're interested. That would be fun. Because I'd honestly just like, if you watch this video and like, I'd honestly just love to hear what your thoughts on it. Is it chaos? Is it bad? Is it okay? Don't know. Have to find out. Great. Oh gosh, the chaos of all my Python programs on my desktop. All right, that's all from me. I hope you guys got something out of it, enjoyed it. That was a marathon, that was chaotic, but I guess I'll just have to see what comes of this over the next few days and weeks or whatever. So thank you guys so much for tuning in. I hope you have a great evening, a great Easter break, because that's what's happening for people in schools and stuff at the moment. All right, bye.